So you get notice for recording, right? Okay. Okay, guys, welcome to our class today, Wednesday, March 30th, 2022. And today, sorry, would be our last class. So we'll talk about final exam and the course overall before the end of our class. So we talked in the previous weeks, 2 weeks, week and a half, about the computational complexity and what do we mean by that. So focus on the class of decidable languages. Therefore, from now on, we will assume that all our Turing machines are halting TMs. What do we mean by halting? If you remember, halting means that it has a decision. There is no loop. Even if there is a loop, it will halt. So, and it will have a decision. It will be a decidable. So, definition. Let M be a deterministic Turing machine, DTM. The running time of M is said to be T, n natural number to the natural number, if for all x belong to alpha, beta star, sigma star, M halts in at most O, big O, we call it big O, to the T of the length of input steps. So the main factor in the complexity is the length of input, The space required by M is said to be, so here running time and here is space complexity. The space required by M is said to be Sn to n if to all x the same belong to that alphabet star, M uses at most big O to S, which means space to the length of input. There is another column, there is another parenthesis here. Cells in its work tape. And we said before that in this course, we will concentrate on running time complexity or in time complexity, but sometimes we'll mention the space just to let you know there is a space complexity. There are many complexities could be counted. Remarks. We assume that the 3-tape model of a Turing machine and count the space used on the work tape only. So we assume that in this space complexity that we have a 3-tape model of Turing machine, and the space used, we count the space used on the work tape only, the tape that we are working on. We always count the amount of resource used as a function of the input length. So if we are talking about resource complexity, we will use the same, and all of those depending on the length of the input. Since we use the big O notation, we ignore multiplicative constants and lower order terms. For example, if we said that this algorithm or this method or this problem took from us big O to n plus 2n, we will say it's a big O of n. And we clarified that before also. So, time and space complexity classes, we'll talk about time, then the space. Let t equal n from natural number to natural number, a function from natural number to natural number. The d time is t of n, where L, there exists a deterministic Turing machine having running time t of n. and it accepts L of M. Time and space, it is the same. Recall that in non-deterministic Turing machine, the Turing machine can non-deterministically branch off at every step. So at every step during its computation, it can non-deterministically decide to do one of two different things. So if we have NFA, non-deterministic finite automata, we have multiple paths, and I clarified that many times. So it will run those paths at the same time in parallel. So to decide, we'll do one of two. It will have more than one computational path which will lead to either accept state or reject state. So these are the two things. We are looking for a path that will lead us to accept state or to reject state. That means it decides on that path. So let n be non-deterministic Turing machine. The running time of n is said to be the function t from natural number to natural number for all x belong to every computational path in n, halts in at most big O t to the length of x, which is the length of input steps. N time is t to the power n for the language L. There exists a non-deterministic Turing machine n having running time t of n such that L equal L of n. So these are the definitions and the function definitions that we have. So we define those functions in the handout. So here is another clarification to make sure that you understand these derivations of the function. The classes P and NP, also we have those on the handouts. We said the class P equal the union for k greater or equal to 0 to the function time for n to the power k. NP equal the union for k and time for n to the power k, which is almost the same. P is widely recognized as the class of problem having an efficient solution. So P, we said that P for a problem that we already know an efficient solution, and we prove that it's P. And P is said to be the class of problem whose solution can be verified efficiently. And I talked about this in the previous class and the class before. We said the class NP, it's a complex problem, but if somebody bring a solution for me, I can verify it efficiently. So what are the examples? For P, matrix multiplication, sorting an array, computing minimum spanning tree of a graph, shortest path. Those are problems. I know that we can find the solution. Oh, there is a solution and efficient solution for them. For MP, for example, for MP, like some optimization problem, if somebody bring me a solution, I can verify it efficiently. But finding a solution is not an easy step. Alternative definition of NP. Assume that we have a language L, which belongs to sigma star for a certain alphabet, is said to be in NP if there exists constants C greater than 0 and K greater or equal to 0, and a deterministic polynomial time Turing machine V, also known as verifier, V to refer to verifier, such that for all x belongs to alphabet star, x belongs to L, if and only if this symbol mean there is exist y belongs to alphabet star, then and the length of y is less or equal Cn to the power k v of x and y equal 1, which mean 1, that mean accepts. V, it is a verifier, deterministic polynomial time Turing machine that take two strings, input x and a string y. So it will take input x and a string y. Y, we call it a certificate or proof. A string whose length is a polynomial in the length of x for the length of x equal m. Example, in order to understand what we are talking about. Example 1, graph isomorphism problem. The graph isomorphism problem. If you wanted to read about this problem, you can go and see Wikipedia. But it's about a graph isomorphism. So let G1 is a graph 1, has vector and edge V1 and E1, and G2 graph 2 has V2 and E2, B2 graphs. We say that G1 is isomorphic. This is the symbol of isomorphic of G2. So if there exists a bijective function, what do you mean by a bijective function? It is a one-to-one function and onto function. This you should know about it in math. You don't know, you can go and just search what is bijective function. You can see a short YouTube to clarify this. F, a function f, has V1 and it will lead me to V2 such that for all uv belong to V1. U and V belong to E1 if and only if f of n, f of V belong to E2. At that time, we said the graph is isomorphic. So G1 or GI, which means graph isomorphic. So I have a pair G1, G2, and G1 is isomorphic of G2. NP algorithm for graph isomorphic. So the input of this algorithm, the first graph and second graph, the certificate f V1 will lead us to V2. Verifier's algorithm, input G1, G2, and f. One, it check if f is a bijective function. If not, will reject. For every pair u and v belong to V1 square, check that u and v belong to E1 if and only if f of n, f of v belongs to E2. If the check fails for any pair, then reject, else accept. Now, suppose that G1 and G2 are isomorphic. Then there exists some function, bijective function, we mean, that will satisfy step 2. If not, either 1 or 2, they will not be isomorphic. So graph isomorphic is NP. It's one of the complicated problems. Then we hear a complement of NP. If this problem is NP, what is the complement of it? It will be the language L, where the complement of that language belongs to NP. So is NP equal the complement of NP? Is NP equal P? Also, those are, we talk about this one, but also here, is the NP equal to complement of NP? Those are also two problems of the open problems in computer science and mathematics. We don't know. We don't know. By graph, if we have a class NP, the class of complement NP, some said that P will be at the intersection of those two. Still, we don't know. It's open problems. Then we talk in the next handout about NP completeness. L1 polynomial time reduced to L2, denoted as if L1 is reduced, this one less or equal with P, that means it's reduced to L2. If there is a polytime computable function, Fn belong to sigma star and it will lead us to sigma star. If x belongs to L1 and if and only if f of x belongs to L2. L is contained in sigma star. L is said to be NP hard. If for all L prime belongs to NP, L prime could be reduced to L. L is NP complete if L is NP hard and belong to NP. Based on those, we have the first theorem. If L is NP complete and L belongs to P, then P equal NP. Okay. So how we prove that? L prime belongs to NP. L prime could be reduced to L via F. So if we input X via F, we'll get the result of F of X. We will input this to a poly algorithm. We know it's a poly algorithm for L, and it will give me yes or no, then I can accept or reject. This is polytime algorithm for L prime. Theorem 2, if L1 could be reduced to L2 and L1 is NP hard, then L2 is also an NP hard. Using the lemma, you remember the lemma? Let L1, L2, and L3 belong to sigma star. If L1 could be reduced to L2 and L2 could be reduced to L3, then L1 could be reduced to L3. So the proof of that, if L1 could be reduced to L2 via F, same as here. L2 could be reduced to L3 via G, same another function, same as here. Here, we'll put X, f of X could be reduced to G of f of X, and thus will be equal h of X. Then h of X equal G of f of X. Then L1 could be reduced to L3 via function h. If X belongs to L1, that means f of X belongs to L2 and h of X belongs to L3. X1, X does not belong to L1, then f of X did not belong to L2, and although h of X is not belong to L3. H is a polytime computable since F and G are polytime computable, and we say with the summation we'll count one complexity. If this is a polytime and this is a polytime, then this will be a polytime also. So let L prime belong to NP. L prime could be reduced to L1 since L1 is NP hard. L1 could be reduced to L2 assumption. Then L prime could be reduced to L2. Then L2 is NP hard. Then we talk about Cook-Levin theorem, and we talk about SAT problem. What is SAT problem? So it is Boolean satisfiably problem. A Boolean formula is a formula defined inductively over Boolean variables and the gates and or and not. So I will use the three gates and or and not. For example, x1 or x2 prime and x3, or x1 or x2 complement or not x2, and x3 bar or x1 bar and x2 bar or x4. So with this one, we'll have a truth assignment. Tau is an assignment of values 0 or 1 to each Boolean variable. So tau, x1 equals, assume that we have exam. Calculate tau. x1 equals 0, x2 equal 1, x3 equal 1, and x4 equal 0. What is the output of x1 or x2, etc.? So it would be 0 or 0 and 0 or 1 and 0 or 0. So it will be 0 and 1 and 0. And you know, with and they have to all to be 1 to have 1. Since we have 0, it will be 0. We see that a Boolean formula phi, this, is satisfiable if there exists a truth assignment tau such that phi of tau equal 1. So it is satisfiable if the phi of tau equal 1. So sat equal phi, where phi is satisfiable. Phi of tau equal 1. So here in these formulas, we have literal, which is a variable, xi or xi bar. A clause is an OR of literal. These are the clauses. This is a clause, this is a clause, and this is a clause. A 3CNF formula is an AND of the clauses where each clause has 3 literals. So here in our example, we have 2 literals. With 3CNF, we should have here 3 literals between them and OR. Then the clauses connected with AND clause, with AND formula. So the 3 sat phi, where phi is a 3CNF satisfiable Boolean formula. Sat can be reduced to 3 sat. 3 sat belongs to MP. Certificate would be the truth table tau. Check if theta of tau equal 1. If so, then accept, else reject. And we talk about the problem click in the handout. So click, it would be 2 graph GK. G has a computable graph of size K. So the K the size and G is a graph. 3 sat could be reduced to click. So if we have input phi, L11 or L12 or L13, we said it's 3 CNF, which means that each clause has 3 literals. And L21, L22, L23 to LM1, LM2, LM3. Construct G, which take vector and edges as follow. V, Vi, and J, where I greater or equal to 1 and less than M, and J greater than 1 and less than 3, because we said we have 3 literals in each clause. H, which is the vertex of I and J prime, I not equal I prime, and L of ij is not equal L of I prime J prime. Set K equal M. The output would be the graph J and K. This is the click. In order to clarify, what do I mean by click? That each node should be connected all to other node except itself or its complement. We will see how. Okay. So theta or phi, x1 or x2 prime or x3, and x1 or x3 prime or x4 x3 sorry, or x4 prime, and x2 or x3 prime or x4. So this is a clause 1, this is a clause 2, this is a clause 3. These are the literal x1, x2, x3, and their complements. So here, this is a clause 1. We have x1, x2 prime, and x3. Clause 2 here, we have x1 prime, x3, and x4 prime. Clause 3, we have x2, x3 prime, and x4. So see here, x1 is connected to x4, to x3, and x2, and also it's connected to x4 and x3, but it's not connected to x prime. You see there is no line to here. x2 prime connected to x4 and x3, and to x4, x3, and x1, but it's not connected to x2. There is no direct line between it and this one. x3 the same. It will be connected with all x's except x3 or x3 complement. Is that clear, guys? Is that clear? Do you have questions? Tammy, you ask about this one, or you mean here L prime? Here? No, we said that L prime is an NP problem. So is L prime could be reduced to L1 since L1 is NP hard, and L1 could be reduced to L2 by assumption, then L prime could be, yeah, normally it's the complement, yes. L prime would be the complement. So is this clear? Questions? How the clique could be connected, that each clause could be connected to all other literals in the graph except itself or its complement. So phi is satisfiable because we can connect each one to the other one. There exists a truth assignment that gives value 1 to at least one literal pair clause. So at least each one of them could be connected to one literal pair clause to the other one, to one literal from every clause, gives a complete path. So x1 is connected to clause 2 and clause 3, x2 connected to clause 1 and to clause 2 and clause 3, x3 connected to clause 2 and clause 3, and vice versa. So guys, what does that mean? Some of you will say to me that could those cannot be connected? In some cases, yes. If I put here like x1 and here x1 and x1 prime. So sometimes it could be happen in logic, but with most of the cases it's connected, and this is the clique graph. So since the number of clauses equal to m, therefore we have a complete graph of size m. If G has a clique of size greater or equal to m, same as K, then G has a clique of size m. Consider the literal corresponding to this clique. So set values to the variable such that each such literal get a value 1. This assignment is satisfying assignment for phi, then phi is satisfiable. So if we can have by this connection has each clause end with 1, with and, then we will have 1 at the end, and this will be satisfiable based on the theory above. So the course is end. Thank you guys. It was nice time with you. And now I'm open to your question for the last class notes. Other than that, we will start talking about the final exam, then we will have a general discussion. Questions? It seems no questions. Shall we start with final exam? Okay, Colin. So the final exam will be in a form almost similar to the midterm. So we'll have multiple choices, we'll have true, falses, and we'll have some solving a question. We might have a question for short definitions, same as in the, I'm not sure, assignment 2 or 3. Like 1 line or 2 line. It shouldn't be identical, same as handout. Just understand what you are writing about. So the final exam will contain of multiple choices, true, false, and the answer would be on the paper. and some solving questions. There's a tutorial for your group assignment, coming tutorial. I will send an announcement about it, and also a tutorial for final exam material. And those would be held in person. Those would be held in person. So I'm not sure when is the coming tutorial. I think it's Friday. We have a tutorial for the group assignment. You have to go to the course plan announcement that sent on January 31st. So group assignment would be April 1st, this Friday. Yes. This Friday. So I will send the announcement right away after the class. And there is also next Friday, the Friday after would be the final exam revision, which is April 8th. What do you mean, Alexander, by all kinds of question cumulative? What do you mean by that? No, the whole entire course. You know, we cannot separate the material. You know, the material is like we're building a chain for deterministic, non-deterministic. You see, then regular expression, then context-free. They are all connected to each other. I'll send an announcement about the final exam. Don't worry. That the material, what we covered since day one. And guys, I wish you all the best of luck. I wish that all students do well, same as they did in the midterm. If you have any question, any comment about the course, so I can improve my teaching in the future, I'm open to your comment. Don't hesitate to talk. So Laura, do you have any comment, anything you want to say? I'll take one by one.
No, I'm good.
You are good. Okay, Zachary. I cannot hear you very well. Zachary, can you repeat? Oh, I'm good, thanks. Okay, Zachary, thank you. Megan? Megan Ginham? Just unmute your mic and start talking. Seems she's not here or... Okay, Madeline? You are good, okay. Colin?
No, I'm all right. I don't have anything. I just really appreciate how accommodating you've been in terms of, you know, starting lectures, you know, 15 minutes later to accommodate for, you know, in between online and
Person, yes.
and in-person classes. But beyond that, no, thank you.
You are welcome. You are welcome. Tammy?
I'm okay, thanks.
Thank you. Alex? Alexander? All good, thank you. Nicholas?
Yeah. One thing
Yeah.
that might help me would be maybe instead of just like actually working through some problems, instead of just reading through them, I find it helps when I can actually see them being like written down.
I understand the course. You know, it's a math that you are not get used to it, right?
Mhm.
But you know, we are talking the basic level of computation, which is the most difficult thing to understand. But I think in tutorials that the TA is solving problems for you guys, right? Unless you don't attend the tutorials.
Yeah, okay.
So if you attend the tutorials like this Friday and next Friday, the TA there to solve a problem. I know this would be a challenge, but this is what is in our hand. However, even when I taught this course in person before COVID, it's kind of a course that new in concept and all of these things to your mind. So I told you from the beginning, it's very abstract course, which is the type of math there depending on the graph theory and the set theory, something you are not get to use it in your daily life mathematics. Wouldn't be an easy, but I tried my best to make it as much as simple as I can. I totally understand and agree with you, Nico.
Okay, thank you.
You are welcome. Aaron? You are good. Brandon?
Oh yeah, I just wanted to say the same kind of thing as Colin. Like, thank you for being like super accommodating. And then I was gonna mention kind of the same thing as Nicholas. Like, I understand that a lot of the concepts are as abstract, so like introducing them requires you to read off of slides. But maybe for like an example or two, you can like walk through them with the class, like and like kind of write it down live. Like that way it's like a combination of both with respect to what you were saying before. If you understand what I mean.
Yeah, I understand totally.
Mhm.
I'll work in this maybe in the future when I
Yeah.
teach this course again.
For sure.
I already ordered. I feel this is needed. That's why I ordered this one, the writing board to be written with online. Unfortunately, it was supposed to be delivered like beginning of March. However, I still didn't get it.
But yeah, that's all that I really wanted to say. Thank you.
I feel that I need this in order not writing a class note to write it immediately live in front of you. I believe this would be more helpful to students in the future.
Yeah, it could be like accommodating for people with like different learning styles, if you know what I mean.
Yeah.
But yeah, for sure.
Thank you for this comment. Appreciate it.
No worries. Thank you so much.
Thank you. Eloy? Eloy Lam?
Oh, I'm just here to listen into the conversation.
So no more comments or? Okay, Eloy. Did I miss anyone? If I missed anyone, just let me know. Okay, guys, it was nice to meet you all. I wish that I meet you in person. I love to see my students, but sometimes with COVID maybe learned us some new techniques to deliver courses with some family reason that I cannot be in campus. But I enjoyed teaching you the course. Thank you for your comment. It was very helpful for me. Okay, Megan, if you wanna talk, go ahead. Okay, you are all good now. Okay, thank you, Megan. So I enjoyed teaching you guys, and I wish you the best of luck. I hope that I did well in the course. Always, as instructor, we're trying to get this feedback in order to improve ourselves. It's a continuous improving process, always. So the first time I taught this course, I learned from my students. Then second time, I tried to improve. Also with you, I tried to improve with more class notes and all of these things, which I find it's a bit helpful. Then I find that this board would help. I order it, but unfortunately it's not. It was supposed to arrive end of February, beginning of March, but till now it's not delivered. You know, the shipping thing and this thing will go all around the world, which delay shipping. So, but for sure it will be here sometime soon. So next time it would be available. So it would be very helpful for a student to follow with me while I'm writing, like live writing. So it would be more helpful for them. Guys, we receive an email today. I'll share it with you. I'll share my screen to ask you to. Okay, I'll share this. It is from, yes. Can you see the email now? Okay, Zachary, thank you. So please direct your student to complete their SQCT by going to feedback.uwo.ca. So just as we receive the email from the feedback team, that they open the course feedback form or the course evaluation form, whatever it is more convenient. You can go to the feedback.uwo.ca. I believe you receive an email for this. So it's good thing to have also your comments or some student who did not attend to write their feedback there. That would be very helpful for us and for the university to improve the overall teaching process. Just since they ask us this first year, they ask us to say this. Sometimes they were sending us separate email to say this, but in this year, they include it in the first email. So please do it in your free time. It will not take from you a lot of time. And it's very helpful for your colleagues that will take the course next year. I don't have any more thing. I'll send an announcement towards the tutorials, the next two tutorials, and also for the final exam. Wish you the best of luck in your group assignment and in your final exam. I'm sure you'll do very well, and hope for you all the success in all your courses and your final exam. And after that, I wish you a happy summer break. Thank you all. If you have something, you can stay and talk with me immediately, directly. Otherwise, hope to see you in some other courses next year. Bye for now.
Thank you so much.
Thank you. Thank you. Thank you, everybody. Zachary, Tammy, Zachary, Laura, Eloyd, Colin, Megan. Tammy, do you have anything? Megan, thank you, guys. This is the end of our course. Bye for now.